Morning, Che.
Morning. Only 5 of y'all here today. Do y'all know where your friends are?
No idea, Che.
Not really, no.
How are y'all? Are y'all still okay? Or are y'all burning out? Are y'all? What's the status of?
Yeah, quite okay. I think it'll get worse towards exams.
Okay. How are the other subjects? Okay.
Yeah, sure.
All right, I guess.
Teacher, how was your weekend?
My weekend was good. Yeah. I've been trying to go to the park. That helped a bit rather than staying at home around 4 hours. So that helps a little bit.
Nice.
Are y'all exercising a lot at home?
Yeah, sure.
You'll have to exercise, okay? Keep your mind a bit more awake. Okay, CK is here. Daman is here. Yes, here. Just okay, we will wait a couple more minutes and then we will start, okay?
Okay, sure.
Okay, sure.
Okay, let's start, yeah. Okay, so this is from May, June 2016, variant 4.2. Okay, let's look at question 1. Object moving in a straight line at constant speed, force applied to the object. What is the possible changes in the motion of the object? What can happen to an object?
Just slow down, speed up, stop.
Yeah, so any two, it can accelerate, it can decelerate, it can stop. It can also change direction. So, yeah. In this case, 2 marks, so you can put two changes, two possible changes. Okay. Okay, I have a skier taking part in a speed competition. The winner of the competition has the highest average speed over the 100-meter section. Starts from rest and has a constant acceleration, reaches a speed of 60 meters per second in 16 seconds. Okay, what is the acceleration that you get?
So 3.8 meters per second squared.
Yep, 3.8 meters per second square. Okay, next one. Over the length of 100 meters, the time recorded is 1.85. What is the average speed? What did you all get?
54 meters per second.
Yeah, 54 meters per second. So just total distance over total time, because they ask for average speed.
Mm.
100 meters. 100 divided by 1.85. Why does the skier bend his body? Explain your answer.
So to reduce the air resistance acting on his body.
Yes, correct. So
Should
when,
I have a
Raman, so when you reduce air resistance, what happens then?
Actually, you speed up.
Yes, so you have to add that. So to reduce air resistance so that you can speed up.
Okay, sure.
Yes, James?
So can we say he has a lower center of gravity, so he's more stable?
Yes, you can say that as well.
Okay.
Lower the center of gravity, it's more stable, it has more balance. Okay. Okay, 2 railway trucks on a track. I have 6,000 kg moving at 5 meters per second. Truck B is 5,000 kg, which is stationary, so no velocity. Okay, calculate the momentum of truck A. What do you all get?
Should 30,000.
Yes, so you take mass times velocity. That's how you calculate momentum.
Yeah.
And then the trucks collide, buffers compress, and they bounce off each other, remaining undamaged. After the collision, truck B has a momentum of 27,000. Determine the impulse applied to truck B.
So impulse is changed in momentum, right? Okay.
Change momentum.
So then, isn't it just 27,000?
Yes. So it will be 27,000. If you all have any questions, ask me and I'll just go through the answers. The trucks are in contact for 0.6 seconds. What is the average force?
So 45,000 newtons.
So you take the momentum change divided by the time. Then you get force. So 27,000 divided by 0.6, you get 45,000. Calculate the final speed of truck A.
Um,
So I take the momentum from 2A, which is 30,000. I minus 27,000, I get 3,000. Okay, and then they ask for speed. So I take 2,000 divided by 6,000. Yeah. So it says that after collision, they bounce off each other. They don't collide together back again. So the question says the final speed of truck A. Wait, let me just take down some information and then I will switch to the board. Okay, so we want the average speed. We want the average speed of truck A. Okay, so we know truck B was 5,000 kg. We knew the momentum for truck B was 27,000 when we calculated. And then we see that truck A is 6,000 kg with 5 meters per second, and it had, before collision, it was 30,000. So we know that principle of conservation of momentum states that the momentum before collision equals the momentum after collision. So what's the momentum before collision? What's the momentum before collision?
just 30,000.
30,000. We get 30,000 from this times this.
Yeah.
This is stationary, so this times this equals the value of it. And then after collision, they don't stick together, trolley A and trolley B. So they will have separate momentum. So if you look at trolley A, the momentum is 6,000, and we don't know what's the speed, that's what we want to find. And then for truck B, we calculated just now, 27,000. And we just shift it around and we're able to find the speed of truck A. So if you move this side, it will be 3,000, 30,000 minus 27,000. That is equals to 6,000 V. And V is equals to 3,000 or 1,000. 0.5. Okay, you understand?
Yes.
Okay. So that's speed for truck A. Okay, figure 3.1 as a cabin transport passengers. The cabin is attached to a cable which moves horizontally from A to B, then up the hill from B to C. There is electrical input of energy which moves the cable. Place 2 ticks against type of energy that increase as the cabin moves horizontally at constant speed. So what is the energy that increases? Which one would it be?
So the internal energy of the surrounding and internal energy of the biomass.
Yeah, so internal energy of surroundings and internal energy of wires of motor. So the last two. Because this is when it's moving horizontally. Okay, cabin and passengers have a total mass of 800 kg. Vertical distance is from B and C is 50 meters. Okay, so this is now 800 kg. And from B to C is 50 meters. It's stated here. So what is the increase of gravitational potential energy of the cabin and passengers when they move from B to C? How to calculate gravitational potential energy?
So mass times gravitation, mass times gravity times height.
Yes, so mgh. The mass will be, how much is mass?
800 kg.
4 times with gravitational acceleration, which is?
10,
And what's the height?
50,
You get 400.
1,000 joules.
Okay, it's quite straightforward. CK, okay? Can follow?
Yeah, sure.
Kezia?
Sure.
Okay. The rest I can hear you. Okay. Okay, the cabin then descends back from C to B. It's going back down. The weight of the cabin pulls the cable, which rotates the motor. The electric motor acts as a generator when rotated in this way. What are the environmental and economic benefits of this arrangement? When the weight of the cabin pulls the cable, that rotates the motor. And the electric motor will act as a generator when it is rotated. So it gives the power. When the motor is rotated that way, it gives the power to move the cabin as well. So what is the environmental and economic benefits?
Sure, like it acts like it provides power, so it saves costs.
Yeah, okay, correct. So generating electricity without really with using kinetic energy basically from the rotation of the motor. So that saves cost because you don't have so much of external power.
So they don't have to use fossil fuels, so it's reducing pollution.
Yes, correct. So that would be an environmental benefit. Okay, so when you answer this kind of questions, right? So it says environmental and economic. So you must give at least one of each. Okay, because they want both, and then you got to explain your point as well. Okay, and then so it's cost effective, and then yeah, pollution. Okay, so yes, that is that. Any questions so far?
No, sure.
No.
Okay. Archaeologists investing shipwreck discovers a wooden box on the seabed. Okay, and then I have this box. The dimension of the lid is 1.2 by 0.8. Pressure of the atmosphere is 1 times 10 to the power 5. The lid is 15 meters below the surface of the sea. The density of seawater is 1020 kg per meter cube. What is the pressure on the lid of the box? So not on the base, but lid of the box due to the seawater. So at the top here, what is the pressure? So what formula do we use?
HPG.
Can you speak louder? I can't hear you.
Sorry, HPG.
Right? Times with the density, times with the density of the water, of the seawater, and then times with 10. So you should get 150,000. Okay, so that will be the pressure on the lid. H rho G. H is height, rho is the density, and G is 10 meter per second. Okay, the total pressure on the lid. So what would the total pressure be? So I have pressure acting on the lid. That is what we found before, which was 150,000. And then what do I need to add it to? So I have, okay, let me switch the border. So I have the box and the pressure acting at the top due to the seawater is what we calculated just now. So that will be H rho G. Which we calculated to be 150,000. Okay, and then now it asks for total pressure. So what do we need to take into account now when it's total pressure? Look at the question. How do we calculate total pressure? I already have the pressure acting on the lid because of the water. What do I take into account for total pressure?
So the area.
No.
The pressure of the atmosphere.
Yes. So you have to take into account the pressure of the atmosphere, atmospheric pressure as well. So the 150,000, I must add up with the atmospheric pressure. Okay, so plus 1.0 times 10 to the power of 5. So I add this with this. Okay, and you should get 250,000 Pascal. Okay, because they're asking for the lid again. It's the same thing, but just now we calculated this, but that was the pressure due to the seawater, just the seawater only. So we take the density of the seawater here together with the height and everything. But the total pressure, you must take into account the atmospheric pressure, which is given as this, to get the total pressure acting on the lid. Okay?
Yeah.
Okay, let's look at the next one. The downward force that the total pressure produces on the lid. So we're looking at force now. The downward force that the total pressure produces on the lid. So there's pressure on the lid. So what will the downward force be being produced on the lid? So how do we do that? So I have this. I have pressure acting on the lid. And now I want to calculate the force that is acting on this. So what is a formula that relates pressure with force?
The pressure equals force over area.
Yeah, pressure equals to force over area. And it says here total pressure. So total pressure means you must take the pressure from the second answer, not from the first answer, from the second answer. So going back to my board. I have and my pressure is equals to force over area. And I'm now calculating for force. So my total pressure is 250,000. What I want to calculate. What is my area of the lid?
It is
0.96. Show it off.
What is my area? How to calculate the area?
0.96.
What do I multiply? What?
So what's that?
Calculate the area. What am I multiplying?
So 1.2 meter with 0.8.
1.2 times 0.8. So switching back to that. Okay, so 1.2 times 0.8. Then I bring this over to the top. And I will get my force. So 250,000 times 1.2 times 0.8. How much do I get? 240,000. And because this is in force, what will my unit be? What's the unit of force?
Newton.
So that will be my force acting on the lid due to the total pressure of 250,000. Okay. And the last question for question 4. The force needed to open the lid is not equal to the value calculated. So the force here was 240,000, but then to open the lid, the force will not be 240,000. Why? Why will it not be equal to the theoretical value? When we calculate something, we are putting it in an ideal situation. So theoretical value and real life value, real life force, real life pressure will be totally different. So in this case, why will it be different?
So the lid could be heavier.
Okay, the lid could be heavier. What else? It is in the water, so there is water resistance present. So the theoretical force like I said earlier, is in an ideal situation, not taking into consideration friction and water resistance and drag and all that kind of stuff. So in the seawater, there will be drag, there will be water resistance, and these things will result in us having to apply a bigger force to overcome those forces. So water resistance friction, and then pressure inside the box, because now it's in the water. There is pressure inside the box, and then
Sure.
yes,
So doesn't it vary if the box has water inside it compared to the box having no water inside?
yeah, it will vary as well.
Sure, but then they don't state if there's no water or there's water, so we can presume.
Yes, you can say that the pressure could be different inside the box.
Okay, sure.
Okay, anyone has any other answers?
No, sure.
Okay, can go and take a quick break. Come back in 10 minutes. Okay, then we'll continue. All okay? All okay to take a break?
Yeah, sure.
Okay. Okay, come back at 9:50. Okay, let's look at the next question, yeah? I have 2 pans containing water placed on the hot plates of an electric cooker. They're switched on, the temperature of the water in the pans start to increase. When the temperature is below 100 degrees, some water is evaporating. At 100 degrees, the water starts to boil, temperature remains constant. State and explain which pan has the greater rate of evaporation of water when both pans of water are at the same temperature.
The larger pan,
Why the larger pan? Explain.
because it has a bigger surface area.
Yeah, so the surface area of water exposed for evaporation is larger for the large saucepan. Okay. Apart from the temperature at which it occurs, state how boiling differs from evaporation besides the temperature.
So boiling means like a specific point of the liquid, then only will start to boil.
Okay. Whereas
Then evaporation can happen at range of temperatures.
okay,
So bubbles will form in boiling, but not evaporation.
correct. Yes, that too. Boiling, another thing is it requires heat. Evaporation, no. Okay.
So can I say that boiling occurs throughout the liquid,
Yes. Whereas evaporation,
only at the surface?
correct. That's correct. So boiling is throughout the liquid, but evaporation happens at the surface. After the first layer of the water is evaporated, then the second layer is exposed for evaporation, whereas boiling is throughout the liquid. Okay. When the water is boiling, thermal energy is being supplied to the water at a rate of 920 watts. Okay. Explain the effect on the molecules of the thermal energy supplied. What happens to the molecules? When thermal energy is being supplied to the water? What happens to molecules when they gain heat?
So they get faster,
Yep, they move faster. Why?
so they have more energy,
What type of energy?
kinetic energy.
So they start moving faster. They start moving apart, and they start escaping as well the surface, and they have more because they have more kinetic energy. Okay. Okay, but in this case, right, once the water is boiling, so when the water is boiling, the molecules are already moving apart. Okay, they are already, because it's already boiling, water's boiling point is 100 degrees Celsius, so they're already moving apart. So when thermal energy is applied on top of that, they're not just moving apart, and they're not just moving like faster and all, they're also starting to escape. Okay, it's also starting to escape from the surface and everything, which is why the whole they evaporate and everything. They become bubbles and the steam is produced. Okay. Now, specific latent heat of vaporization of water is 2.3 times 10 to the power of 6. Calculate the mass of water that boils away in 5 minutes. So I use what formula?
E equal ml.
Okay. What is my E?
Should the energy?
Yeah. So what's the value?
Should do 920 watts.
Okay. So if I take 920 watts, then what do I do after that?
So and then times it with the L.
Times. Think again. Switch to the board. Q equals to ml. That is what I want to find. So I don't know what that is. My latent heat given is 2.3 times 10 to the power of 6 moles per kg. Q is equals to, we have power of 920. The time. I have 5 minutes. 5 minutes is how many seconds? Because Q is equals to IT. No, Q is power times time. Sorry. So my power is 920. My time is 5 minutes. 5 minutes is equals to how many seconds?
Just 300.
100 seconds. So my mass will equal to 920 times 300 divided by this. And I should get, what do I get? Because Q is equals to power times time. So I have to take the power times with the time given, which was 5 minutes. So after doing this, what is the mass? What do you all get? The mass? How many
120 grams.
Yeah, 120 grams, 0.12 kg. Okay, so that is the mass. Okay, so remember Q is equals to power times the time. So you have to times with the seconds. In this case, it will be 300 seconds. Okay. So 0.12 kg.
So I still copy.
Oh, sorry. Just Okay.
Teacher, I'm done.
Anyone else still copying? Still copying?
No, sir.
Okay. Then we have question 6. First, superimposing the path of a ray of light. Light is traveling in glass through the boundary with air. Okay, so I have glass and going to air. So denser to less dense. Using the protractor, measure the angle of incidence of the ray of light at the boundary with the air. So, how many degrees is it? How many degrees when you measure?
25.
Sorry?
125.
135? No.
25.
100.
Just 35 alone.
25.
20,
25 is what it's saying.
25. So from 55, I'm going to 90. So it should be 35, not 25. Okay. So from the normal, from this ray to the normal. The normal is here. Let me just draw. So the normal is here. So this angle here should be 35 because from 55 to 90 is 35. Okay? Next. The refractive index of glass is 1.56. What is the angle of refraction? So I have 35 as my angle of incidence. I have refractive index of 1.56. What is my angle of refraction?
54.6.
Okay. So I use refractive index n equals to what? What is the formula I'm using?
Sine I over sine I equals to n.
My is 1.56. Then I have sine of 35 divided by sine r. Sine r, I bring it here. Okay. You should get after rounding off, you should get, what did you all get again just now? What did you all get?
So R equals
0.
63.
Sorry?
R equals 63 degrees.
Just now someone got with a decimal, what was it?
0.368.
Is it 21.6?
21.6. What did you all get? So someone got 21.6, was it? Let me check out. Sine 35 divided by 1.56.
At 21.5 degree.
And I should sine, I inverse myself. What did you all get? Can you all tell me what?
21.5.
21.1.
21.5 something.
I got 31.5.
31.5.
21, teacher. He said 21.
So make sure this is 35, not 25. Then divide 1.56. Then whatever answer I get here, I have to shift sign that answer. I got 21.57 to 21.6. Did anyone get a different answer? What does the answer scheme say? Answer scheme says 63. I don't think that's right. Did everyone get 21.6 or 21.57?
Yeah.
Yeah? Okay, you should get this, yeah? Okay. What is meant by critical angle? What is the definition of critical angle?
Teacher, bent at 90 degrees.
Sorry?
I think
I didn't hear you say it.
it's like bent at 90 degrees.
Okay. So how do you put it in proper words?
Show when the angle of incident align with the normal.
It's aligned with the normal.
So I think so. So I'm not sure how to put it into words.
Minimum value of the angle of incidence at which total internal reflection can occur.
Okay, total internal reflection happens when the angle of incidence is above the critical angle. Okay, so there's two different things now. Let me explain. So let's say I have a block. This is my normal. Okay, so this is glass. Let's say this is a glass block. And then this is air. Okay, so now let's say I have a ray going in.
Teacher, isn't it when the angle of refraction is 90 degrees?
Yes. So if I have a ray going in, okay, now glass going to air, denser to less dense. So the refracted ray will be towards the normal or away from the normal?
Away.
Away from the normal. So you're going to get something like this. Okay. Then when you start increasing this, so my angle of incidence is now here between the ray and the normal. So when my angle of incidence starts increasing, okay, this ray is also going to move. So let's say I take another marker pen. So what's happening is when this increases, this is also going to increase a bit more, and it's going to keep increasing. And then at some point, this is going to be 90 degrees to the normal. So it's going to be like that. When this is exactly 90 degrees to the normal, let's say at an angle of here, this is the critical angle. So critical angle is the angle of incidence when the angle of refraction is 90 degrees to the normal. Or 90 degrees, like that's what it means. So critical angle, very important terminology for definition. Critical angle, we first have to say it's the angle of incidence. That's the first thing you have to, there are two points that you need to have in the definition. It's the angle of incidence when the angle of refraction is 90 degrees. So what is critical angle? Critical angle is the angle of incidence when the angle of refraction is 90 degrees. Now, total internal reflection happens when, okay, when I keep increasing it beyond the critical angle, then total internal reflection will happen. So total internal reflection happens when the angle of incidence is greater than the critical angle, then total internal reflection happens. Total internal reflection doesn't happen at the critical angle. It's above the critical angle, larger than the critical angle. At the critical angle, it will be 90 degrees. Beyond the critical angle is total internal reflection. If it's lesser than the critical angle, then it's just normal refraction outside of the medium. Okay, can you understand?
Yeah, sure.
Yeah, so remember our total internal reflection occurs when the angle of incidence is greater than the critical angle. Then total internal reflection happens. When the angle of incidence is bigger than the critical angle. At the critical angle, the angle of refraction is 90 degrees. So for your definition for the question, you must have these two. It is the angle of incidence when the angle of refraction is equal to 90 degrees. Okay? Okay, going back to the question. Calculate the critical angle of light in glass of refractive index 1.56. So what formula do I use for critical angle?
Just sine C equals 1 over n.
The sine of the critical angle is 1 over the refractive index, 1 over n. So again, I have this formula. I want to look for the critical angle. My refractive index is 1.56. Critical angle will be inverse sine of 1 over 1.56. So what do you get? One divide 1.56 and then shift sign of that answer. What do you all get?
39.87.
So, yeah, so 40 degrees.
Yeah, so the decimal would be 39.8 degrees. So you can approximate the value to 40 degrees Celsius, 40 degrees, sorry. Okay, so you should get your critical angle to be 40 degrees. Okay, I have a water wave crossing a boundary from shallow to deep. Okay, shallow water going into deep water. This is the process that takes place at the boundary between the shallow water and the deep water. What is the process called? What is this? What's happening here?
Refraction.
Refraction. Pick one box corresponding to the property of wave that is same in the shallow. So from shallow going to deep water, what is one property of the wave that will stay?
Frequency.
Yes, the frequency will stay the same. The rest will be different. Okay. So that is question 6. Okay, I'll give you all a 5-minute break, then we continue. Okay? So we'll start at 10:20 again.
Okay, Chair.
Yeah, sure.
Yeah, sure.
Okay, so I saw this funny video on YouTube, so I thought I would share with you all. It's a bit long, but let's just watch it for a while. And then, do y'all get easily disgusted? Do y'all get easily disgusted?
No.
Do any of y'all like would vomit if y'all see something or
No, sure.
no? Okay, how about the girls? Kezia and Mushiga, do you easily gag or not?
I don't think so.
Yes? No?
No.
No. Okay. One video is funny and one video is
So they said no.
we'll look at the funny one first, okay? And then we'll look at the disgusting one later. Okay. So I thought that was really funny lah. It's a long one. We'll see until wherever you want to watch. Okay. Okay. Can y'all see?
Okay, sure.
Can see, yeah?
Yeah.
No, it's not starting.
The vibe. Oh, what the hell?
现吧。如果爱情真伟大，我有什么好挣扎？难道我比别人差？是谁要周末待在家，对着导人，别以为导人在我就不敢打你。
Okay, so that was one. Okay, now we will look at the disgusting one. Okay, have you all heard of mukbangs or not? Do you all know what mukbangs are?
Yeah.
Yes.
Okay, so it's like these people eating like crazy amount of foods lah, and then some of it looks really good. And then some of them they do challenges where they eat like maybe like 100 McDonald's nuggets or something. And then the whole idea of a mukbang is, if you all don't know, is that they don't do any cuts. So throughout the whole video, they just eat, and then they either talk to you or you just stare at them eating lah. So some of them are really good. Like for example, she's eating fried chicken. And mukbang started in Korea, so they started this whole thing. So and then now the Americans do it a lot lah, but they do it with their own American food and whatnot. Okay, and then there are people who do crazy things like eating like live stuff. I tried to choose the less disgusting one lah, hopefully, because I don't want any of y'all to like vomit or anything. But yeah, so I thought this is interesting just to see what people actually eat. Like I personally wouldn't eat stuff like this lah, but they're quite daring. So yeah. And like this. It's crazy. If you need me to stop the video, please let me know, okay? I'm not sure what this is. Do you all know what this is? I have no idea.
No, sure. Sea snail?
Yeah, they seem to be enjoying it. I mean, she seems to be enjoying it a lot.
Jesus.
It's okay because it's dead, but then the idea of eating it raw is also a bit weird. But yeah. It's crazy lah. I don't know how they do it, but it's just interesting to see how they can eat stuff like that. And they seem to be enjoying it, like genuinely enjoying it. This is not so bad lah. Like, okay, I will show you another one lah in a while.
Jeez, yeah.
Would y'all eat stuff like this? Are y'all
No.
people are daring, like they would want to try it. I know people who actually want to try it. Would y'all eat it?
No.
Eaten sashimi before.
Sorry? What?
Yeah, I've only had octopus once.
Okay. Like the cooked ones, you've never eaten them?
Not sure, it was raw.
Oh, you've had raw octopus before?
Yeah, it was not great. They can still move, even.
Oh.
Yeah.
Wasn't it scary to eat it?
Huh?
Wasn't it scary to eat it?
Kind of. It got stuck to the roof of my mouth because the suckers.
I don't know what. I don't even know if I want to know or not. And then there's one more. Sounds quite weird lah. Again, I don't know. I thought people in
Well, hello everyone, how is everyone doing in this mesh out there? Today we are reacting to mukbangs. Now, I've made a video on mukbangs before, and I said in that video I really want to make a part 2 because I have been watching a lot of mukbangs, guys, and I have come across this girl. We saw her in the last video, so young. All right, whatever her name is. Oh my goodness, this girl's the craziest, guys, because she like gets the animals and the fish and like kills them right in front of you and then proceeds to eat them. Okay, the amount of stuff that she eats is crazy, guys. She eats literally anything. Okay, so in this video, she is preparing eels and mudfish. Now, she doesn't just get these eels already dead. Oh my God! Oh my God! Can you imagine this? Before you eat this thing, she's grabbing them. Look at this, guys. All right, these eels don't know what's going on, trying to escape. What's going on? Oh my God. Okay, so those were eels, and these are now mudfish. All
Everyone okay? Yeah? Everyone getting like nauseous?
No.
Yeah? Okay.
Number 1, put all the eels and mudfish into one big container. Oh, it's getting out. This is so bad. This is so bad. Oh my goodness. First step is to put it all in this container, and then I think she adds salt to the container to
Wow.
so I guess season it, I guess. Look at them, he's trying to escape! Oh my God, ew! Oh no, guys, look away. Oh, here comes the salt. Oh my goodness. Oh, they're just poor fish are just dying. How is this on YouTube, guys? Oh, look at this eel looking at her. Oh, don't eat it. Oh my goodness. Oh, okay. Well, there you go. And now she's just prepared everything. Ooh, doesn't look too bad now that I look at it. That's what I'm talking about. All right. She does these crazy things, but then she prepares it, and then you look at it, and I'm like, okay, all right. Maybe I will try eel and mudfish next time. Okay, all right. Okay, guys. All right. I think the most shocking thing for me is that she, shows you what it looks like before. So this is her eating this shit. Yeah, very entertaining. But I'll show you some other shit that she cooks on her channel. Oh my goodness, guys. This is what she's gonna do. She's gonna kill squid. Oh, look at them. They're all squirting and peeing. Guys, all right. This girl's crazy, man. Okay, so here she has a live squid. A live squid. This squid's barely breathing in this water. Oh my goodness. Oh, look how they stick to your hand. Oh my goodness. Does squid squirt ink? Or is that octopus? I don't know. They have ink in them, I think. Oh, look, there it is. It's black now. Oh no, guys. Okay, look away, because I'm pretty sure she's just gonna go straight in for the chop. Okay, she's gonna cook the legs first. Oh no, okay. Oh, poor squid. Oh god. Oh god. It's okay. Look away, guys. Look away. Oh, that's it. It's over. He had a body and a life a second ago. Is that a pee? Yeah, I think that's the squid peeing. Probably because it's so scared. So I heard that if you put salt on fish, it makes the muscles, spasm out. So it looks like they're alive right now. But all it is the salt and their muscles reacting. That's what I read. This girl's crazy, guys. All right, she's going to first cut off the legs. Okay, I think she's just going to eat it just like that, guys. I'm not even going to lie. I think she's that crazy. Look how it reacts. Creepy. I think she's gonna eat it. Go on, eat it. Oh my god! Oh, God. It just was alive. It's definitely squishy, a bit crunchy, a bit tough. Oh my goodness! And then she proceeds to cooking the rest of the squid. Just got it. All right, but I'm not gonna lie, guys. All right, look, even ink's coming out. But yeah, I'm not gonna lie. The way that she prepares it, she makes it look really good. Oh, well, there you go. It looks pretty good. All right, that's steamed squid, and that's squid sashimi, which I'm guessing is raw. She doesn't look too bad now, guys. I'll try it. Damn, I've never had squid before. Never. Oh wait, no. I've had calamari, so I guess that is. It makes you think before eating this animal that died. We know when you actually do get to see it die. But the Koreans, guys, they don't give a shit. Look how happy she is right now. She's like, okay, screw it, all right, it was worth killing them right in front of me. Yeah. Oh my goodness, she brought a whole crab. What is this? Is it still alive? It's still alive. Oh, bruh. Oh my goodness. Okay, it actually looks, damn, look at the meat in that thing. Holy, okay, that actually looks pretty good. Holy crap.
Yeah, Koreans, they can really eat. They might look really tiny, but they can eat a lot of food. I don't know how they do it, but yeah.
This poor crab. Oh, what is that? Where did you get that from? Korea? What a 5 kg king crab. I bought this from the market in the early morning today. Damn. The fact that you just go to a market to get this. Jeez, look at this. Its face. Let me see the tongue. Oh my goodness, how are you even gonna cook this thing? This poor crab. Oh, once alive, now look at him. It looks really, it looks so good. I feel bad. I feel so bad for these poor animals, but it's not my fault that they look so delicious. But it's not necessary, okay? It's not necessary to eat this kind of shit. I mean, it looks fun to try. I don't know. Oh man, okay, it does look fun to try. Oh my goodness. I mean, I don't mind the legs. The legs look good. All right, you could pass me a few of those little crab legs, but the middle part. Oh, look at them.
Okay, yeah, that's pretty much what I wanted to share. There's a lot of crazy stuff that they eat. There's a lot of people like to eat squid, and then the ink squirts out and all that kind of stuff. But yeah, I just thought it was just interesting to share, because why not? Would you all do stuff like that? Anyone daring enough?
Nope.
No?
So not raw.
Not raw, okay.
Yeah, not again.
Okay, fair enough. I personally wouldn't do it. Yeah. So yeah, these are things that people do, and then they get 1 million views, just like that. And then they become rich and famous. But yeah. Okay, let's go back to the paper. Okay. Okay, describe the use of X-rays in a security application. Include a diagram. Do you all see the thing?
Gotcha.
Hang on, my screen just it's lagging. Just a moment now. Okay, while I wait for it to get back to normal. Use of X-rays in security application. What would it be?
To check for hidden weapons,
Yeah, so
illegal objects.
yeah. So if you go to the airport, so sometimes they ask you to put your bags and all and stuff in this. And then they run through and see if there's any harmful substances and chemicals and like bombs or anything like that. Okay. Yeah. Okay. Draw a straight line from each wave to the most appropriate speed. Okay. So let's see. Radio waves in air, what is the speed? Which one would it be?
Should 3 million meters per second.
So this one?
3 million.
Yeah. Let me just draw. Okay, so here. And then ultrasound in air?
300 meters per second.
So this one. And X-ray in vacuum?
So isn't that one also 300 million?
So this one as well. Okay, so those are the speed of the waves. Okay. And then we will finish off this question, and then I want to go to last week's question on the ray that I asked you all to complete so that we can discuss that in class. So yeah, I'll just quickly finish off this question and then we will go to that one. Okay, and then for the rest of the questions, oh, I'm actually done with questions. Okay, I will post the answers on Edmodo for the rest of the paper, and then you can check your answers, and then you can ask me if there's any questions. You can ask next week, right? Okay?
Okay, sure.
To last week's paper that I told you all to do on this one. Yeah. So I have this. This is paper 6, by the way. Okay. So I have I want to investigate. The class is investigating refraction of light passing through the transparent block. A student is using optic pins to trace the path of ray of light. So it shows the student's ray trace sheet. Okay, if you all have the paper printed, which I hope you all do, you all can do it on the paper, because I think doing it on the screen would just be a bit off. I'm gonna try and do it on the board. So just give me a moment to draw it, and then we'll go through. So basically, they've given you a set of instructions, and you just have to follow. It's not difficult to do, but we will do it together. Okay. Yeah. So just give me a moment. Let me draw the thing on the board. Okay, so let's look at the question. So I have, it says on figure 2, draw a normal at the center of side AB. Okay, and then label the line NL and label the point E where the normal crosses. Okay, I'll tell you what, I'm going to put this in these instructions in the group so that we don't have to keep looking back and forth, so that you can refer to the question separately as well. Okay, I'm going to take a picture of it so that you can see my board. Okay, so I'm going to switch to the board now. Okay, so I've roughly drawn. Please remember that my drawing is not to scale, so it might be a bit different, but when you do it on your book, you should get it. Okay, so the first question, it says draw a normal at the center of side AB. I have the center AB. I have the side AB, draw a normal at the center. So you measure and then you see which is the center, and then you draw the normal. Okay, and then you label the line NL. Can everyone see the board?
Yeah, sure.
Okay, and then you label point E where the normal crosses AB. So where the normal crosses AB, they ask us to label it as E. And then label M where the normal crosses C and D. So C and D, where the normal hits this line CD, you put it as M. Okay, so far all okay?
Yeah, sure.
You can do it on your paper together while we are doing it. Now it says draw a line above AB. So this is AB, above AB, to the left of the normal. So this is the normal, the left will be here. At an angle of incidence 30 degrees to the normal. So angle of incidence, as we all know, is always towards the normal. So you have to measure 30 degrees and draw the angle of incidence. Okay, and then label this line FE. So this line, this is E, so F is here. So the line FE. So that will be my angle of incidence. My FE is the line for my incident angle. Okay, and then next it says label the positions of 2 pins P1 and P2 placed at a suitable distance apart on FE. So they're saying on the line FE, you place pins P1 and P2 at a suitable distance apart for accurate ray tracing. You want to put 2 pins on line FE. So let's say P1, P2 will be here. So it must be at least about 5 cm apart. Okay, that's the standard way of doing it now. So make sure your P1 and P2 is 5 cm apart. Okay, I should use red. If your line is too short, you just extend it. Just make sure it's about 5 cm apart. 5 cm or more, at least 5 cm. Okay? So that is the next one. So that is A. This is all A, part A. So far, all okay?
Yeah, sure.
Okay. Now, next one, B. The student observes the images of P1 and P2. So P1 and P2 is the object. So it's observing the image of P1 and P2 through side CD. CD is here, CD of the block, so that the images P1 and P2 appear one behind the other. So when they're looking at the image, I think the eye is somewhere here, if I'm not mistaken. I forgot to draw the eye. The eye is here, yeah. Now let me just draw it. Okay. Okay, so the eye is here. So they're observing from here such that P1 and P2, the image, when it's here, it's also back. One is in front of the other. One point is in front of the other. Okay, he places 2 pins, P3 and P4, between his eye and the block, so that P3 and P4 and the images of P1 and P2 are seen through the block and they appear one behind the other. So P3 and P4 is already marked. So now it says, draw a line joining the positions of P3 and P4. So join this line basically. So again, you'll have to use a ruler and join them. And it says, in the question it says, continue the line until it meets the normal. Okay, so draw the line and continue until it meets the normal. Label this point K, so it meets at K, so this is K. Okay, measure and record the angle between the line joining P3 and P4, so this line, and the line KM, this is KM. So the angle will be here. So you have to measure this. So it says measure and then you have to record it. So you measure. Okay. What you should get is, let me just check the answer scheme. If you do it correctly, you should get, if you do it accurately and all, you should get the angle here to be between 28 to 32 degrees. So the angle should be between 28 to 32 degrees if you do it correctly on your book. Okay, so that's where you measure and record. And then it says, measure and record the length x between M and K. So between M and K is these two here. And again, if you do it correctly, you should get between 20 to 24 cm. So using your ruler, you measure between K and M. You measure the line KM. Okay? And then you write it down. So that's what they're asking you to do. And then they also say that they repeat the procedure with angle incidence 50. So instead of 30 at the top, they use 50. and they get the angle of refraction to be angle of reflection to be 52 with the distance of 19. So based on your results, you have to see if the angle should always equal to the angle of incidence, the angle that you calculate, and then you justify your answer. Okay, so yeah, so if you get around there, so your approximate value will equate both angle of incidence and angle of reflection. Okay, which will also justify these values here. Okay. Yeah. So which will bring your statement, to be matching lah. Angle of incidence equals to angle of reflection. Okay.
Okay, sure.
Yeah. And then precaution to be taken. You want to make sure you use when you draw, right? So when you draw things like this, you must make sure you use thin lines when you draw. Make sure because the lines will affect if it's too thick of a line, then your angle of incidence, your angle that you're measuring might be too small because your lid is too thick. Make sure the pins are far apart. The P3, P4, P1, P2 must make sure that it is far apart, because if it's too near, it will give you an error when you're trying to align the ray of light. So those are some precautions that you want to take. Okay. So those who want to complete the drawing can complete. I'll give you all a few moments to do that. Okay, anyone has any questions?
No, sure.
No? Okay, the other part, I think there are 3 more questions on the paper that we did before this. I will upload the answers on Edmodo, and then you can check your answers. And then if you have any questions, you can ask me, or we can ask me on Edmodo, or we can discuss during our next class or so. Okay? Yeah?
Okay, sure.
Okay. If you have no questions, then that is all for today's class. I will see you all next week. Yes,
Okay, thank you, sir.
Okay, thank you. Bye.
Gotcha.
Bye, sir.
Bye.
Bye.